All right, so taking a look, we're going to start talking about our other kinds of roots. We talked about real roots last time. Factor them, solve them, you get your real roots, they cross the x-axis. This time we're going to talk about irrational and complex roots, because those are the other kinds of answers we could get for our polynomials. So starting with our first example we have here, h of x equals x to the fourth plus 8x squared minus 9. How many possible roots do we have there? 4, because it's a fourth degree polynomial. So we are going to have 4 roots for that one. So part B, they want us to actually find the roots. So I'm going to take my equation, and I'm going to set that equal to 0. So just like we were doing last time, we'll factor it. So how is this going to break apart? Perfect. X squared plus 9. X squared minus 1. So then I'll set both of those equal to 0. So with my x squared minus 1, I add my 1 over, square root both sides, and what do we get? X equals plus minus 1. So there's 2 of our roots. We got positive 1, we got negative 1. Other side, though, I'd have to subtract my 9 over. So I would get x squared equals negative 9. I take my square root of both sides, and what do we get? Plus minus 3i. So we still have 4 roots here. We have positive 3i, we have negative 3i, and then we have positive 1, we have negative 1. So part C, where it tells us to describe the roots, we have 2 reals and 2 imaginaries. Your imaginary roots and your complex roots are always going to come as a pair because of the conjugates. So if you have positive 3i, you are definitely going to have negative 3i because they can't go anywhere without the other. So same thing happens with your complex numbers. If you have positive square root of 7, negative square root of 7 is going to go along with it too. So you're always going to have groups of 2's for those ones. So then part D, sketching our graph. We'll start off with the 2 real roots that we can actually put on the graph, so positive 1, negative 1. Imaginaries don't hit the x-axis, so I can't account for those. I can't put them anywhere. I can figure out my y-intercept. So if we look at our equation, what is our y-intercept? Negative 9, so I'm going to go down to negative 9. What would our behavior be? It's a fourth degree with a positive leading coefficient. They should both be going up. And again, that's really all I have to go off of so far. I have the imaginary, or I have the real roots, I have the y-intercept, and I have my end behaviors. So I'm just going to sketch my parabola with the information that I have. So let's check this. Let's see how we did. In your calculator, under your y equals, type in our equation. Let's see if our graph matches the graph in the calculator. Does it match? Yep, that's exactly like what we just drew. All right, let's try again. Next example, x cubed minus 8. So part A, how many possible roots? 3, because we have a third degree. So part B, let's find those roots. Now I know past practice you're going to want to add the 8 over, take the cube root of both sides, and then you're going to tell me the answer is 2. That's not going to work anymore. That only gives you the real root. There's more than just the real root here, so we got to factor this. This was our first day of factoring. You have perfect cubes here. We have x cubed minus 2 cubed. Remember, 8 is actually 2 cubed, so we've got to factor using our difference of perfect cubes. So the way that formula went is you would start off subtracting your two cube roots there, your x and your 2. It's always the same sign since this one was subtraction, the first one's subtraction. Then in here it's the first squared, so x squared. I do the opposite sign of what is in the first one, so since that was subtraction, it's going to be plus there. Multiply these two together, so 2 times x gives me 2x. Always positive, and then it's your last one squared, so 2 squared gives me 4. So again, x is my first, 2 is my last. So it's first minus last, first squared, first times last, last squared. That's always the pattern it goes in. The only thing that changes is this sign and that sign, depending on whether you're adding or subtracting. So first one, that one's pretty easy to figure out. That just gives us x equals 2, so we have one real root there. Can we factor x squared plus 2x plus 4? No, because the only way you can multiply to get a 4 is 2 times 2, in which case it would add for 4 in the middle, or 1 times 4, which would give you a 5 in the middle. So I'm going to use completing the square here. You could use quadratic formula, but since it's an x to the first, I like to use completing the square. I think it's a little faster. What number is going to go in our space? 1. Let's get back into this one. So we were starting our completing the square in our second example here. So left side over there becomes x plus 1 squared. Negative 4 plus 1 gives us an equals to a negative 3. Square root of both sides, and we get plus or minus I radical 3 on that right side. So that's square root of the negative 3. The negative becomes I. 3 stays under the radical. So then we just subtract our 1 over. So negative 1 plus or minus I radical 3. So describing our roots, we have one real root and then 2 imaginaries. The negative 1 plus I radical 3, and then the negative 1 minus I radical 3. So the next part, sketching the graph. Again, not too much we can go off of. We have our root at positive 2, so I'm going to put that on there first. Looking at our equation, what is our y-intercept? Negative 8. So 1, 2, 3, 4. And then we got our imaginary roots. That's not going to really do much for us. Because it's a positive leading coefficient in an odd degree, that means the left side should be coming from the bottom. Right side should be going up. And because it's a degree of 3, you don't want to make it look like a straight line. You want to have kind of a little curve to it. So I kind of curve it around the y-intercept there so that I can connect up to my root of 2. Then go ahead, type that equation in your calculator. See if it matches what we just drew. How do we do? Good. All right, taking a look at our last one. Let's try this one more time. So we've got our function here, f of x. This is the original function. Because we have an odd number of terms there, you can't really do factor by grouping or anything, so they're helping you out by saying that that factors into those 2 trinomials right there. So they're kind of trying to help you out a little bit with that. So looking at either the one in standard form or the factored one, how many possible roots are we going to have? 4. 4th degree, or adding up those 2 together. So 2 plus 2 tells us we're going to have 4 possible roots here. So let's go ahead and find them. I'm going to start with the factored form. So my x squared minus 2x plus 5 times my x squared minus 6x plus 10. So our first trinomial, is that factorable again? Nope. So I'm going to go with completing the square. So what number is going to go in our space? 1. So we have x minus 1 squared equals negative 4. Square root both sides. Add your 1 over and we get 1 plus or minus 2i. Are we going to be able to graph that on our x-axis? No, because they're imaginary. So let's figure this out for the other side. So again, I'm going to set that trinomial up to do completing the square. What number is going to go on the line this time? 9. So I get x minus 3 squared equals negative 1. So I square root both sides, add my 3. So we get x equals 3 plus or minus I. So all of our roots for this one are imaginary. We don't have any real roots. Don't have anything we're going to be drawing on our x-axis here. So the only two things that we really have to go off of is our y-intercept should be at 50. So I'm going to use each line, I'm going to count as 10. So 10, 20, 30, 40. Let's say that one is 50. And then the only other thing we have to go off of also is our end behaviors, because it's an even degree positive leading coefficient. Which way should they both be going? Up. Really, you just kind of end up getting a little parabola looking like thing there. So questions on those? Algebraically, we can find our imaginary and complex roots, but we can't actually graph the imaginary ones. All right. Let's take a look at the next page. So next thing we're going to do is we're going to go backwards. We have our graph this time. They want us to write our equation that goes along with it. So when you are writing your equation, you're just going to list out the set of factors. You're not going to actually multiply them out because you got to take into account all the different multiplicities that go along with it. So when you're trying to create your equation, here's your list of things to consider. What is the shape of the graph? So you know which degree you're looking for. End behaviors, zeros. What is your multiplicity of your zeros? Those kinds of things. So let's take a look at our first graph here. Based on our end behaviors, what kind of a degree should we have? Even or odd? Odd. This one's going to be odd because left side is down, right side is up. So we know we should have an odd one. Will our leading coefficient be positive or negative? Positive. So we know degree should be odd. Leading coefficient should be positive because of the way our end behaviors are going. So now let's take a look at where our roots are. We have one here at negative 6. We have another one at negative 1, positive 4, and then positive 8. Those are where our zeros are located. So what would be our multiplicities on these zeros? Negative 6, would that one be an even or odd? Odd. We always assume the lowest when we're writing these equations. So we're going to assume that that's just going to be to the first power. How about the negative 1? What would the multiplicity there be? Even. So our lowest even would be 2. So we're going to assume that that one's going to be squared. How about for the 4? Odd because it crosses through, and then the 8 would also be odd. So our equation, f of x equals, if our root value is negative 6, remember the factor is x plus 6, it changes the sign value. And then we would have x plus 1, but that one would be squared because it bounces, and we said it had even multiplicity. And then x minus 4, and then x minus 8. So again, just always checking. If I add up my degrees in my factored form, 1 plus 2 plus 1 plus 1, that gives me 5, so that works. That's an odd degree. Would our leading coefficient be positive with the way we have written things? Yeah, so we are good to go on that one. All right, let's try it for the next one. What kind of a degree would we have? Yeah, degree should be even. Leading coefficient should be positive. So let's take a look. We have a root here at negative 5. What would be its multiplicity? 1. We have another one here at negative 2. That would have a multiplicity of 2. And then we have another one here at positive 2. That one would have a multiplicity of 1. So our equation, negative 5 would become x plus 5. Then x plus 2 squared. And then our x minus 2. Now, neither of these had a negative leading coefficient, but if you had one, all you would have to do is stick a negative 1 out front. So if that leading coefficient needs to be negative, you just put that negative 1 out in front of it, and that makes that end up being negative. This, however, didn't need it, so we don't put it there. This next page, this is one we've actually done before. We did this back with our quadratics, but I just figured we would review it quickly. This is if you're writing just a quadratic equation specifically. So you don't have to do a whole polynomial where it's higher than a degree of 2, just doing a quadratic. This was our sum product rule. So here is the equation that we talked about before. X squared minus the sum times x plus the product equals 0. That's all we have to use in order to be able to write our quadratic equation. So, looking at our first example, if you're given the two zeros, actually add them together. So what is negative 5 plus 13? 8. Multiply them together, so negative 5 times 13. Negative 65. So then our equation, again, we're just going to follow along with this. It would be x squared minus the sum times x plus the product, but my product here is a negative. So do I have to write plus negative 65? No, generally they don't like to see that, so we would just write it as minus 65. And that's all you have to do for your quadratics. Add your roots, multiply your roots, plug it into the formula. All right, let's try it for the next one. So negative 1/3 plus 3/2. What does that give us as a fraction? So product, multiply the two of them. Negative 1/2. So our equation, x squared minus the sum times x plus the product, but again, our product here was negative, so it'd be negative 1/2. But that's not the way you're going to see the answer. They're not going to write it with those fractions in there. We have to get rid of the fractions. Does anybody have an idea of how we could get rid of those fractions? Not decimals. They don't like decimals either. What is the largest denominator we have there? 6. So I'm going to multiply everything times 6. So 6 times x squared gives me 6x squared. 6 times my 7 over 6 gives me 7. 6 times my negative 1/2 gives me a negative 3, and then it equals 0. If you have fractions, you got to get rid of those fractions by multiplying by whatever the largest denominator is. And then this is the answer. So our third one there, we've got one of the roots is 5 minus 2i. So what is the other root? 5 plus 2i. Remember those conjugate pairs. If one of them's there, the other one is also there. So our sum, our i's just end up canceling, so our sum should be a 10 for that. Product. The nice thing about conjugate pairs is you only have to multiply the firsts and the lasts. So 5 times 5, negative 2i times positive 2i would be negative 4i squared. What is negative 4i squared simplified to? Positive 4. So 25 plus 4 gives us a product of 29. So our equation would be x squared minus 10x plus 29. All right, so 3 plus the square root of 7, that's one of our zeros. What is our other one then? 3 minus the square root of 7. Again, conjugate pair, so if one's there, the other one is always there too. So add them up. Square roots of 7 cancel. Multiply them out again. Since they are conjugates, you multiply the firsts. 3 times 3 is 9. Multiply the last. Negative radical 7 times radical 7. Negative 7. So we have a product of 2. So x squared minus 6x plus 2. Always minus the sum plus the product. So then our fifth one here, it wants us to write a cubic equation, and they gave us the 3 roots, 2, and then 4 plus 3i, and then 4 minus 3i. So what you want to do is start with writing the quadratic using your 2 i's, and then multiply everything out with the 2. So find the sum first of the 4 plus 3i, and the 4 minus the 3i. Our 3 i's cancel, so we have a sum of 8. Product, multiply them out. 4 times 4 is 16. 3i times negative 3i gives us a negative 9i squared, which that simplifies to, that becomes positive 9, so plus your 16 gives us a 25. So our quadratic would be x squared minus 8x plus 25. That's our quadratic using those 2 imaginary roots. We have that third root there at 2, which remember, if the root value is 2, that means the factor was actually x minus 2. So we can leave it like this, or we can multiply it out. But all of our other polynomials, we left them in the factored form, so we can leave that in factored form. So all of the other examples we did when we were writing the equation, our a value was a 1. It's not always going to be a 1. If you look at the generic equation here, a is that number that is in front. That is your leading coefficient when we're writing our polynomial equations in factored form. So what's going to happen, let's take a look at our first example. We have determined the equation of a quadratic whose roots are -3 and 4 and passes through the point to -50. Express your answer in standard form of ax squared plus bx plus c and verify your answer by creating a sketch of the function on the axes below. So if we do like we were just doing before, and we just write it in factored form, so that would simply be x plus 3 times x minus 4. Type that in your calculator. Let's see if that hits the point to -50. So if I look at my table, oops, does not hit to -50, hits at 2 -10. So that tells us that our a value is not going to be a 1. So we actually have to figure out what this number is going to be. So again, we know we have roots at -3. I'm just going to put those on there because I'm going to have to sketch it. They told me that I had to sketch it. So using the point that they gave me, I need to figure out what that a value is. That's what's missing. I got to figure that out. So I know from my point I have -50 is my y. 2 is my x, so I'm going to plug those in. So in my parentheses, 2 plus 3. That makes that a 5. 2 minus 4 makes that a -2. So if I multiply those together, 5 times -2 gives me a -10, and then times my a. So divide by -10, and what does a equal? 5. So our equation would be 5 times x plus 3 times the x minus 4. But that's in our factored form. They wanted us to put it in standard form. So what do we have to do with our x plus 3 and our x minus 4? Multiply those out. That's x squared minus x minus 12. So once we multiply those out, distribute your 5. So you should have 5x squared minus 5x minus 60. Then go ahead, type that one in and check in your table. Make sure that hits the point to -50, since that's the one we were looking to hit. And there we go, to -50. So that's going to be our actual equation now. So to finish off our sketch, we have a y-intercept at -60. That is our constant value from our equation. I know I need to hit the point to -50. So then there's my sketch. Got my roots, my y-intercept, and then my point to -50 that they told us. So whenever you get a problem like that where they give you your roots, they give you another point, that's kind of your hint. Your a value is not a 1. You should play around to figure out what it's supposed to be. So here, consider the quadratic polynomials in this form. A times x plus 2 times x minus 5. What are the two x-intercepts of this polynomial? -2 and +5. So if I sketch a picture of this first one, x plus 2 times x minus 5, I have negative 2, and then 1, 2, 3, 4, 5. I have that 5 over there. Even though it's in factored form, if we multiply our two constants, what should our y-intercept be? Negative 10. So if this is negative 50, I'm going to say negative 10 is approximately here. So this graph's going to look kind of like this. So now if we take a look at that second one, it has the same x-intercepts. It's still going to hit at negative 2 and positive 5. But what would this 2 out in front do to my y-intercept? It's going to make it negative 20. So what it's going to do is it stretches our graph down a little bit further. And then our third one there, where would our y-intercept end up being for that last one? Negative 40. So it's going to stretch it down even further. So what you have to keep in mind is even though the roots are all the same, that a value does change it. So if it gives you another point that you have to make sure you hit, you got to calculate what that a value is. Because although they have the same answers, the graphs of them look very, very different. All right, let's try a few more on the back. So this time we're going to create the equation of a cubic in standard form that has x-intercepts of negative 4, 2, and 5, and passes through the point 6, 20. Verify your answer by sketching the cube's graph on the axes below. So this time, even though it's cubic, it's still going to follow the similar pattern. A is going to be your value out in front. We have a root value of negative 4, which means our factor is x plus 4. Root value of 2 means we have a factor of x minus 2, and a root value at 5 means our factor is x minus 5. So we can set up that first part. So now we'll use our point to be able to figure out our a value. 20 goes in for y, and 6 is going to go in for x. A stays as a for now because that's what we're trying to figure out. 20 in for y, 6 in for our x. So 6 plus 4, I'm going to make that a 10. 6 minus 2 makes that a 4. 6 minus 5 makes that a 1. So if I multiply those 10 times 4 times 1, what do we get? 40. So I have 20 equals 40a. Divide by 40, and what do we get? 1/2. So our equation would start off as 1/2 times x plus 4 times x minus 2 times x minus 5. That's our factored form. Did they want it in factored form, though? No. What did they ask for? Standard forms. Take a minute, multiply that out. See if you can get the equation in standard form. All right, so that's what we should have. Unless you change the window in your calculator, you won't see our y-intercept there up at 20. Just remember, your calculator's standard screen only goes up to 10, so you would have to play around with your window to be able to see that whole graph. All right, let's try one more here. Create the equation of a cubic in standard form that has a double 0 at negative 2 and another 0 at 4. The cubic has a y-intercept of 16. Sketch your cubic on the axes below to verify your results. So we know double root at negative 2, so that means that would be x plus 2 squared. And then another 0 at positive 4, so that would be x minus 4. So they told us we have a y-intercept at 16. So what would that look like as a point? 0, 16. So we can use that to help us find our a value. So again, a is out in front. So 16 goes in for y, trying to find a. Put zeros in for our x's since it is the y-intercept. So let's see here. 0 plus 2 is 2, but then squared would be 4 times negative 4 would make that a negative 16a. So when we divide, what does a equal? Negative 1. So there's your equation. Let's leave it in factor form. Just go ahead, type it in your calculator. Make sure it looks like it's supposed to. Make sure it hits the y-intercept and it has our double 0 at negative 2. Should look kind of like that when you type it in your calculator. Because it's got that negative leading coefficient. That means the left side is up this time, the right side's down. Bounces at negative 2, hits your y-intercept at 16, and then goes back down at negative 4. So how would you describe this cubic curve at its double root? What is it doing at its double root? Bounces. That's how we know it's a double root, because it's bouncing at that x-axis instead of crossing through it.